Here is an example to understand the concept of KVAr, or the reactive power. So let's assume this example. There is a horse here on the canal, and it's going to pull a boat with the help of a rope through the canal. Now you can see the boat is over here and the horse is on the bank of the canal. As the horse tends to pull the boat, the boat obviously tends to move towards the bank of the canal, towards this way as shown on the arrow. That's for the obvious reason that the horse is not having, let's say, this to be the horse and this to be the boat, and the horse has a rope attached on it, so it doesn't have dead straight. What I mean to say is the boat is not right behind the horse, it's at a side. So as the horse pulls it, the boat tends to move. But we don't want that. We just want the boat to move through the canal dead straight. Now to move the boat straight, there has to be a compensation made. The horse cannot come inside the water and pull it straight, but there could be some compensation done at the rudder. You can see the rudder position here, where it is kept at an angle so that it can compensate the movement of the boat moving towards this way. So when the horse pulls from a side, the rudder is kept at this position so that the boat moves straight. This is the example. How does it relate to KVAr, or the reactive power? With respect to the horse, the power required to pull the boat, either the horse is in front of the boat or on its side, the power is going to be same. The horse doesn't care whether the boat is on its side or behind it. However, we do a compensation, or we require a compensation which is made at the rudder so that the boat moves straight, and it is this compensation creates the reactive force or loss. I'll call it as loss since it's mechanical, but when it comes to electricity, you can call it as reactive power. As we do this compensation, the water is going to have an extra effect called as friction. So this extra friction has to be overcome by the horse to pull it, or with the same horse force, pulling force, the boat will move slower due to this friction. Thus it is one of the loss, and this is called as reactive power. So with this in mind, we'll see how does reactive power arises with this example. So the first one, as we saw, is due to the friction offered due to the rudder, and the second one, the horse itself. Even though the power produced or the power applied to pull the boat by the horse, whether the boat is behind it or at the side, is same, the full effort, I'll name it as effort, the effort by the horse is not completely utilized. The effort is divided into sidewards reaction plus the straight movement. In simple terms, nothing so much mechanical in it. So the sideward movement is, imagine that you're going to pull a rock, a huge heavy rock. So you're going to pull it straight at an angle. You're standing with the rock here, and you're here, and you got to pull this rock through this, but you're standing at a side. So what you will usually do is you will just try to offer a movement by going this direction. You move this way, you're not moving straight, so your effort is wasted in this direction. Similarly, horse, in order to move the boat straight through an angle, which is here, alpha or phi, whatever you call, the horse tends to apply some effort this way and also this way. So the full effort is divided into sidewards movement like this and the straight movement. However, if the horse is just dead straight of the boat, the full effort will be straight and the horse can move the boat much easier or faster. So this sidewards movement is a component called as reactive force or reactive power or loss. So as I said, just to encapsulate, there are two losses. One is friction and one is the sideward movement. Both these contribute to what is known as reactive power. Now assume this to be the power triangle. Let's relate it to electrical means. So here is the boat and here is the horse. Alright, so the boat over here and the horse is here. If the boat and the horse have been in straight line, the force required by the horse or the effort required by the horse is just the straight line. That's called as true power, or electrically we call it as kilowatt, which is measured or which is required exactly to do the work of moving the boat in straight line. However, there is a sidewards movement, that is the reactive component, that is KVAr. So electrically there is a sidewards effect for the boat to be moved straight by the horse, which is separated or at an angle phi. Since there is an angle between the boat, axis of the boat and horse, since there is an angle, that angle is called as power factor. That's very, very simple. If the boat and the horse are in dead straight line, there's no power factor at all. So just kilowatt is required to pull the boat. But since it is at an angle called phi, there arises something called as power factor, which is the measure of the effort which is utilized to pull the boat. And to select the horse for this job to pull the boat, we term it as KVA, or let's say over here, size of the horse. You can't keep a small horse, a baby horse, calf or something like that to pull such a huge boat. So you got to accommodate both the kilowatt and KVAr to know the size of the horse. So with this KVA in mind, we select the size of the horse to pull the boat of a suitable size. So this is one way to understand the concept of KVAr. Hope you guys have enjoyed this video. Thank you for watching, and there are 2 or 3 more videos which explains the concept of KVAr, which is shown here on the link. Please click that link and watch those videos. And one small request from you all is there's a small like button at the corner of the YouTube screen on the left, so do press the thumbs up button, which I like, because it gives me a feedback which videos you like and which you don't, so that I can improve on my video presentation. Thank you, and do comment, voice your doubts. Thank you for watching.